Hi, welcome to the video called Standard Deviation as a Ruler. In this video, we're going to go through what I think is one of the most important topics of statistics, which are z-scores. And in order to learn about z-scores, we're also going to need to learn about the normal curve. So let's get to it. So in the last video, we talked about how important it is to be able to compare different groups of things. So here is a really good example of how that can get complicated. So the women's heptathlon, which is an Olympic event, actually has 7 separate events in it. And some of them are running, some of them are jumping, some are measured in distances, some are measured in times. They are very different from one another. So it's kind of weird when you think about how you would figure out who the winner of that competition is. Do they have to come in first in every single one of the events? No, that's ridiculous. That doesn't have to happen, right? So we need a way to standardize these performances. And the way that we're going to do that is we're going to figure out how far each of those values or each of those performances is from the mean in that event, right? That standardizes things. So the standard deviation is really going to be a ruler for us. We're going to measure in how many standard deviations something is from the mean, and that's going to allow us to do this comparison. So those distances, the number of standard deviations, that's called the z-score. So a z-score is a simple calculation. We take the person's actual score, whatever it is, we subtract the mean from it. So if you did worse than the mean, that's a negative number. If you did better than the mean, that's a positive number. And then you're going to divide that by this, what the actual standard deviation is. And because z-scores have no units, now we're just comparing positive, negative numbers, maybe even neutral, right? 0. And it's going to allow us to deal with those complicated comparisons. So let's do an example with tests. Let's say you took the chapter 1 test. Your score was a 90. And you found out that the mean was an 88. So that's good, right? You did better than the average. But then you found out that the standard deviation was 4. Well, let's see what your z-score would be. We take the score of 90, we subtract the mean, right? So that's good. You get the positive 2. And you divide that by 4 and you get a 0.5. So your z-score on the chapter 1 test is a 0.5. So your value is 0.5 standard deviations above the mean. Let's compare that to a different test. Let's say on the chapter 2 test, you scored an 80. Okay, so 80, that doesn't sound as good as a 90, right? But it turns out that on this test, the mean was a 75 and the standard deviation was 5. So let's see what your z-score would be for this. So you subtract your score and the mean, positive 5, divide that by the standard deviation of 5, and you get 1. This test, you actually scored 1 standard deviation above the mean. So you could say that you did better on the chapter 2 test when you're comparing it to others, right? Obviously, your score is not as high. Maybe that's not going to help your average as much. But if you're trying to be competitive about this, just think about, well, how did everyone else do? It's really the z-score that's going to tell you that. You did better than the average on both of them, but it turns out even though you had a lower score, you did better than the rest of the group on chapter 2. So some quick information that you need to understand about z-scores. When you are taking a group of data and you're standardizing it into these z-scores, right, it's not changing the shape of the distribution. So whatever that shape was, if you just took those values, rewrote them as z-scores, and then plotted them again, it looked like you'd have the exact same shape. However, your center would change because you actually changed the values, and the spread is actually going to change as well. So we'll get a little bit into that later on. But here's a little number line here just to kind of show you of what that would look like, because your z-scores are going to be centered around 0, because 0 is going to be what the mean is, right? Because if you have a z-score of 0, that means you got exactly what the mean was. And you're going to have some positive values. So 1, 2, 3 standard deviations above the mean. It is important to know that 3 standard deviations above the mean typically is a rare thing to happen. It happens, but you're not going to see everybody in a class have a standard deviation or have a score that's 3 standard deviations above the mean. That just doesn't make sense. In strange sets of data, yeah, you could see this happen, but typically this is not going to happen. So when is a z-score big, right? When does that like have some type of effect when you hear it and you're like, oh, wow, that must be really far away from the mean? Well, it really depends on a few things. So first, we need to know about the data's distribution to begin with. And this is where normal models come in. So normal models are appropriate to use when we know that the distribution was roughly symmetric and unimodal. So in other words, get to drawing here. To be unimodal, that means that the peak, right, exists in only one place. And to be symmetric, well, that would mean that the peak would have to be somewhere in the middle, right? So you're looking at something like this to begin with. So that is the most important thing to think about when you're considering what a z-score is. Are you working with a normal model based upon this type of distribution? So let's talk a little bit more about that. So a normal model is that bell-shaped curve that I just drew. And when we make a model, remember, we're not dealing with the actual data anymore. We're dealing with these new numbers, right? They are called z-scores. But we say that the mean and the standard deviation of the model are now called parameters. They're not the actual average of the data or the standard deviation of the data. These are the mean and the standard deviation of the z-scores. So in a standard normal model, you're going to have a mean, which, by the way, that new symbol there is called mu. Okay, so that's like the special model's mean. That's a 0. And its standard deviation, that's a lowercase sigma. That would be a 1. We'd expect it to be a standard deviation of 1. And when all this stuff is really nice, right, in a perfect world, we have a unimodal distribution that is roughly symmetric, and we're going to have this nice bell-shaped curve with a breakdown of 3 percentages that we like to remember. So we call this the 68, 95, 99.7 rule. And here's how it works. Right there in the middle, right, that's your z-score of 0. This right here, this is whatever your mean is, because that way your z-score would be 0. If you go 1 standard deviation to the left, right, that's -1 as a z-score, and 1 standard deviation to the right, that's a z-score of +1, you get this purple region. It turns out that in a normal model, 68% of your data will fall in that section. Well, why is that important? Well, if we can figure out what something's z-score is, we can figure out what percentile it's in. And percentiles are good for comparing to the entire group. And you're going to see that once we do an SAT example, what I'm talking about. All right, so that was the purple. And then we go 2 standard deviations to the left, right? So that's a z-score of -2. And 2 standard deviations to the right, that's a z-score of +2. That would be the purple and the pink regions. Total, that's 95% of the data. That's almost everything. So we would expect that if something is in the normal model, right, that 95% of data would fall between -2 and 2 as a z-score. So yeah, that's why we say 3 sounds like a rare thing to have. That doesn't mean it's impossible, because if we go out that 3rd standard deviation, right, to the left and right, that right there, the whole thing, the purple, the pink, and the red, that's 99.7% of the data. Still not everything, but we only picked up an extra 4.7% there. So this is what's going to help us do some really nice analysis. But before we jump into it, We just need to understand that not everything is going to be a normal model question. It can't happen, right? Here's an example. Not everything is normal. So here's some real data. Took this from the census. The income of U.S. households in 2018. So I think overall there was like 120,000 households that reported. Here's all of them laid out. We have their incomes on the bottom there. You can see that each bar of the histogram is a width of 5,000. So we have quite a few in the, I'd say the 20,000, 30,000 range, right? Kind of tapers off as we get into the 100,000 area. And then there's this huge bar here at the end, and that's because we couldn't show every single possible income. These were all just grouped together into any incomes that were over 200,000. So it turns out, let's break down all these special things that I've labeled here. It turns out that the median household income is 61,000. The mean household income is 87,000. Well, that kind of makes sense because remember that median is just cutting things in half, right? So cutting things in half at the 61,000, that's about here. That means that half of the data is here, half of it's here. That's because there's a lot of data over here. Turns out that the 8% of the entire set of data is in this one bar. So now here's the interesting part. If you actually looked at the mean right here at 87,000 and figured out how many households were to the left of this mean, turns out 66% of the data is. The standard deviation is actually 85,000, which means that if you go 85,000 to the left and 85,000 to the right, look at that. You're covering almost this entire histogram. Now, go back to this picture for a second. Remember how I said that this was the mean? And if you go one standard deviation to the left, you get half of this purple area. What would that be? 34%. Look at this. Going one standard deviation, it looks like I'm getting 66%, right? This is not, this could not be modeled with the normal curve. And that's because it's skewed. It's not symmetric, right? So if you started acting like, oh, once I take the z-scores of this, I'm supposed to get this set of data, or this type of distribution. No. The first rule, you have to be roughly symmetric and unimodal, okay, to use this normal model. This one's not. It doesn't work that way. So let's go to one that is. So let's do this SAT example. We're going to assume that the distribution of SAT scores is roughly symmetric and unimodal. Okay. We know that the mean SAT score is 500 and the standard deviation is 100. So let me just kind of sketch what's happening here. If it's roughly symmetric and unimodal, we know it looks like this. The mean would be in the center here, 500, and standard deviation is 100. Now, just so we all know, SAT scores go from 200 to 800. So standard deviation, if I go 100 back, another 100 back, and another 100 back, oh, there's your 3 standard deviations to the left, and 3 standard deviations to the right. Right, so SAT scores are definitely the normal model, and we can now use that to answer some really good questions. So we're going to start off really easy. We just want to figure out what a z-score of 680 would be, just so we can practice that. So remember that our z-score is whatever this data point is minus the mean divided by the standard deviation. So let's plug into that. So we get 680 minus 500 divided by 100. We get 1.8. So a z-score of 1.8, we can already see that 680 will be right here. Oh, that's perfect. We would expect that to be a little less than 2 standard deviations away. Okay, so let's see how we can now use that to answer some other questions. Now, what is the student's percentile? Okay, so we know that the z-score is 1.8. Now, if we think about this picture, if the z-score of 0 is right here, that's really that mean of 500, right? And we go 1.8 z-scores beyond the mean, we want to know how much of the data would be in this area of that curve. Now, we don't know off the top of our heads because this isn't 1 standard deviation or 2 standard deviations, right? It's 1.8 standard deviations. So we need a little bit of help to figure out exactly what that percent is. And that's where our calculator is going to come in. So to go from a z-score to a percentile, we're going to use this function on our calculator called a normal CDF. And what that's going to do is let us to find that area under the curve between 2 z-scores. So I'm going to get your calculator out. And on your calculator, you're going to hit second vars. And that's because you're pulling up distribution. And we're going to pick number 2 for normal CDF. So lower and upper are asking you for the 2 z-score cutoff. So remember that picture that I drew? We are looking for the beginning of this graph to 1.8. So this beginning, we need a z-score for that. That's a really, really, really negative number, right? So I'm just going to say it's negative 99. Whatever the beginning is, I just say it's negative 99. So negative 99, lower. Upper is 1.8. And we're using the normal model, so we have a mean of 0 and standard deviation of 1. That's what yours should look like on your screen. We hit enter again, and we got 0.964. And so there's those steps we went through again, just a little reminder what that looked like. So this area, 0.964 of the entire graph being 1. So we would say that this is the 96.4 percentile, or we just would say 96th percentile. So that's how we connect the z-score to a percentile. Okay, one last question. Let's say that we still have the same mean and standard deviation, right? What did the top 10% of students have to score above to be in that top 10%? So we're not starting with the z-score this time, we're starting with the percent this time. Now to be in the top 10%, it'd be over here, right? This part of the graph would be 10%. Well, that would mean that you're above the 90th percentile. Okay, so if I already know that this 90th percentile is important, I must be able to go from the 90th percentile back to whatever the z-score is, right? And you can, going backwards, right? That's like an inverse operation. So that's what we're going to do. We're going to do something called inverse norm, the inverse norm function. It lets us find the z-score that goes with a given percentile. It's in the same area. It's that second vars for the distribution button. And you're going to choose 3 this time. And this is going to pop up. So let's do that. So second, vars, and 3. We want to find where 90% of the area would get cut off. So I'm going to do 0.9 for 90. We're going to leave mu as 0, sigma as 1. Paste that in. And this time I got 1.282. We'll round that too. Okay, so right here, remember, if this was 90%, this is now saying that the z-score would be 1.282. All right, so percentile to z-score, and now we gotta go from z-score into SAT score. Okay, so let's do our formula here. You know, the z equals whatever the value minus the mean divided by the standard deviation was. So this time we know the z. We don't know the original score, but we know the mean and we know the standard deviation. So let's solve this equation. Add 500. And there it is. So I would say that those students, they had to score above a 628 to be in the top 10%. All right, so these z-scores are allowing us to answer lots of nice questions about real life situations. So we'll be working on more of those in class, and good luck on those.